Hello everyone, this is Professor Roman. Let's continue the field theory lectures. We are ready now to embark on our study of Galois theory. And I'm going to begin with some preliminaries concerning symmetric polynomials, courtesy of Isaac Newton. A monic cubic polynomial can be written as a product of three linear factors in any splitting field. So R, S, and T are the roots of the polynomial. And when we take this product, we get a polynomial that looks like this. Ignoring for a moment the algebraic signs, the coefficients are these. And each of these coefficients is in fact symmetric in the roots, R, S, and T. Permuting the roots doesn't change these expressions. This is not a coincidence. And to look at the more general case, let T1 through Tn be a set of independent variables. This polynomial, the analog of the generalization of this cubic, is the product of the linear factors x minus ti. This is called a general polynomial of degree d. And because the roots of this polynomial, t1 through tn, are algebraically independent, this is in some sense the most general polynomial of degree n, and facts that we learn about this polynomial should apply to all polynomials. Now it can be shown by induction, and I'm going to leave that for you to do if you wish, that the general polynomial can be written in this form. Here I've got alternating signs and coefficients S1 through Sn. This is monic, where the coefficients are given by these formulas. S1, which is a function, the coefficients are functions of the variables, is just the sum of the variables. S2 is the sum of products of two at a time. S3 is the sum of the products of three variables at a time, and so on. When you get down to here, we're taking n variables at a time. There's only one way to do that, so we only get one term, the product of all of the variables. These polynomials are called the elementary symmetric polynomials in the variables t1 through tn, because they are in fact symmetric polynomials. And for convenience, I'm going to set S naught of T1 through Tn to 1. This is not an official elementary symmetric polynomial, but it'll be useful in formulas that are coming up. And for the same reason, if we have an elementary symmetric polynomial in m variables, but the subscript k here is bigger than m, well, you can't do this because it would require the product of k of the m variables, and m is less than k. So I'm going to set that equal to 0, again, for convenience. So, except for sign, the coefficients of the general polynomial are the elementary symmetric polynomials in the roots of the general polynomial. And since that holds for the general polynomial, it holds for all polynomials. The coefficients of a non-constant monic polynomial P of x are, except for algebraic sign, the elementary symmetric polynomials in the roots of P of x in some algebraic closure. In particular, here's what P of x looks like And if the roots are R1 through Rn, then the coefficient ck is the kth elementary symmetric polynomial in the roots. Now, we want to prove that the elementary symmetric polynomials, S1 through Sn, in these independent variables are also independent. T1 through Tn is assumed to be algebraically independent. We want to show as a consequence that S1 through Sn are also algebraically independent. This is not terribly difficult, but a bit messy, because we're dealing with polynomials in several variables. So it helps, I think, if we break out some of this in a lemma. Let T1 through Tn be independent variables over a field F, and Sk are the elementary symmetric polynomials in the T's. First, and the elementary symmetric polynomials satisfy this recursion. And you can see here why I added these conditions here. S naught is 1 and so on, because when k is equal to 1, you have S sub 0 here, and I need that to be equal to 1. Also, when k is n, this term has fewer than n variables, so this had better be 0. And so that's why I made those conveniences earlier. Part 2 of the lemma, in the full expansion of a product of this form, so this is a monomial in S1 through Sn, a product of powers of S1 through Sn. When we expand this, this T monomial, when you expand this, it's going to be a sum of monomials in the variables T1 through Tn. This particular monomial, it's T1 to the power equal to the sum of all the exponents, T2 to the power equal to the sum of the exponents E2 through En, and so on, till we get to Tn to the En. This monomial appears exactly once in the expansion of this product. As for the proof of part 1, it's just a matter of applying the definitions of the elementary symmetric polynomials and the two conventions I made. So it's right here, and I think it would be good practice for you to do that yourself. For part 2, we can use induction on the number of variables. When n is equal to 1, then pi here has only one elementary symmetric polynomial, raised to a power. So this is going to be S1 of T1 raised to the E1. S1 of T1 is T1, so this is T1 to the E1, which has indeed this very form. So the result is true when n is 1. Assume, then, that it is true for any number of variables less than n, and n is at least 2. In this product, it's the same, this is pi, capital Pi. In this product, we can replace the elementary symmetric function, I keep saying that, the elementary symmetric polynomial S sub k using the recursion from the first part of the lemma. Now, the monomials, when we expand this, that are divisible by t1 to this power, which is part of the monomial we're interested in. It's right here. The monomials that are divisible by this are the monomials gotten by applying the full power ek to this first term in the binomial. You know, if you expand this using the binomial formula, the only term that has t1 to the ek is the first term. Okay. Pull out the t1 to the ek from this product, and you'll get this first factor in our monomial here that we're trying to show is unique times this expression. But the inductive hypothesis applies to this product. It has one fewer variable and tells us that this monomial, which is, let me grab this again if I can, it's the rest of this monomial from t2 on, that appears exactly once in the expansion of this product. We multiply by this, and it tells us that this appears exactly once in the expansion of pi. I told you it would be a little messy, and it is. I think I've rewritten this several times, 4 times, 5 times, to try to get it as concise and yet hopefully not too confusing as I could. Okay, but with this lemma, we can now prove the main theorem. The elementary symmetric polynomials, S1 through Sn, and the variables T1 through Tn are algebraically independent over a field F. To do this, we will show that any non-zero polynomial in n variables, when we substitute the elementary symmetric polynomials for the variables, we get this expression: this must be non-zero. And that, it takes a bit of thought, but that says that the polynomials S1 through Sn have no polynomial relationship amongst them, which is equivalent to saying that each one is transcendental over the base field with the other ones joined. Okay. So, the lemma tells us that when we expand one of these terms in this sum, in this polynomial, this monomial, I put the coefficient here now, ak, this monomial appears exactly once. But, so a monomial of this type appears exactly once in each term of the polynomial. But these unique monomials here are different for each term in the polynomial. Because if you look at this monomial and look at the exponents, you see that they uniquely determine the individual exponents, ek1 through ekn. And those are unique to a given term. So these monomials that are unique inside the expansion of each term are actually unique in the whole polynomial. So there are terms that look like this when you expand this polynomial. Now some of these coefficients could be 0, but at least one has to be non-zero. And so that term is all by itself in the expansion here. And so this polynomial cannot be the zero polynomial. It does not collapse to zero. The way a polynomial collapses to zero is if when you combine like terms, the coefficients vanish. Well, this is a unique term. It's not like any other term, so it's not going away. Okay, so this is not easy stuff to see, and if you want to pursue this, you want to understand this carefully, you'll probably need to go over this a few times. Okay. Now let's discuss symmetric polynomials in general. A polynomial in variables t1 through tn is symmetric if it remains unchanged under any permutation of the variables. So to be more precise about that, this is symmetric if for any permutation, sigma, of the indices 1 through n, this polynomial is equal to this one. So the only difference here is that I've rearranged the variables. Okay. Now, the elementary symmetric polynomials are certainly symmetric polynomials. And that means that any polynomial in the elementary symmetric polynomials is also symmetric. So for instance, here's a simple polynomial in two variables. I replace x and y by s1 and s2. Now this is a polynomial in the elementary symmetric polynomials. It's this one, which looks like that. It's symmetric in the t's, as you can clearly see. Any polynomial in the elementary symmetric polynomials is symmetric in the variables t1 through tn. I probably should say here, in t1 through tn is symmetric in the variables t1 through tn. Well, so far this hasn't really been very deep, but Isaac Newton, sometime in the late 1600s, realized that the converse of this also holds. A polynomial p in the independent variables t1 through tn is symmetric if and only if it is a polynomial in the elementary symmetric polynomials of the t's. So p of t 1 through tn is symmetric if and only if it can be written as q of s1 through sn. One direction was pretty clear. Any polynomial in s1 through sn is symmetric in the t's. We just went through that here. This is the converse, is the real meat here. Any symmetric polynomial in the t's is a polynomial in the s's. In addition, if this is an integer polynomial, has integer coefficients, so does this. Now, it's a consequence of this fact that the following holds. Let p of x be a polynomial. A polynomial f of x is symmetric in the roots of p of x if and only if it's a polynomial in the coefficients of p of x. What's the relationship between roots and coefficients? Well, the roots are the variables, the coefficients are the elementary symmetric polynomials in those variables. So this is just part A, 2a here is just a translation of this into a specific context of roots and coefficients. In particular, any symmetric polynomial in the roots of p of x being a polynomial in the coefficients of p of x belongs to the same field as the coefficients. This is critical. So for example, if p of x is a rational polynomial, any symmetric polynomial in the roots of p of x is rational. We don't know what the roots look like. They're probably not rational unless p of x happens by chance to split over q. But in general, it's not going to, yet the symmetric polynomials in the roots belong to the base field. And if p of x has integer coefficients, then any symmetric polynomial in the roots is in fact an integer. So, as I said, statement 2 here follows from 1, so we just need, and the earlier result. So we just need to address the hard part here, which is part 1 of Newton's theorem. Now, what is additionally remarkable about this theorem, or about the proof, is that it is an actual algorithm. This is very important. It's an algorithm for actually computing the polynomial q of S1 through Sn. So we can actually find this polynomial. Unfortunately, it's not, it's a recursive kind of algorithm, so it's not terribly practical, but at least for hand computation, but it's of immense value, as we'll discuss later. So, proof will be induction on n. The theorem is true for n equals 1 because T1 is equal to S1. So when there's one variable, T1 is equal to S1, or maybe I should say S1 equals T1, so the polynomials are the same, P and Q. So assume the theorem is true for any number of variables less than n, and let this polynomial be symmetric. By collecting powers of the last variable t sub n, we can write p in this form. Each of the coefficients, p sub I, is a polynomial in t1 through tn minus 1, one less variable, because I pulled out tn. Now, since p is symmetric in t1 through tn, it's also symmetric in t1 through tn minus 1. And because the ti's are independent, each of these coefficients separately is symmetric in t1 through tn minus 1. This is something you may need to think on. But therefore, by the inductive hypothesis, we can express each coefficient p sub I as a polynomial in the elementary symmetric polynomials u1 through un minus 1. I'm using u here because s is kind of taken. It's going to pop up again. And so these are the elementary symmetric polynomials in this list of variables, t1 through tn minus 1. So p of t1 through tn here, we can just replace the p's here by the q's. Each qi is a polynomial in the u's and has integer coefficients if p does. Now, note that the elementary symmetric polynomials si can be expressed in terms of the ui's as follows. S1 is u1 plus tn. u1 is the sum of t1 through tn minus 1. So we tack on this one, we get s1. S2 is u2 plus u1 tn. This looks a lot like the recursion from the lemma, but with different symbols and pulling out Tn instead of T1, but it's the same thing really. Now these expressions can be solved for the u's in terms of the s's and the t's, and Tn specifically. And this is what that looks like. U1 is certainly S1 minus T1. U2 is S2 minus U1 Tn. And this is what U1 looks like. Okay? And so we can continue here and get these expressions for the u's in terms of the s's and T sub n. The last equation gives us this expression. Now we can substitute these expressions for the u's into this guy here. See, the QI's are polynomials in U1 through UN minus 1, so we can replace these U's using this formulas here, and we now have something that looks like this, where the R's are polynomials in S1 through Sn minus 1 and Tn. I want to take a deep breath here, maybe back up a little. And again, integer coefficients if P has integer coefficients. Okay, now, because the R's may involve Tn, this is not the usual way you'd write a polynomial as a polynomial in Tn. So we're going to have to gather together, again, other powers of Tn that appear in the R's, and we can write this. And now you see I've had to change the exponent here of Tn because I don't know what it's going to be. If there's some Tn's in here or higher powers of Tn's here, you could push this exponent up. But the G's are polynomials only in S1 through Sn minus 1. Same bit with integer coefficients. If m is bigger than or equal to n, we can reduce the degree in Tn using this formula. We can express Tn to the n as the negative of all the rest of this, shove everything on the other side, and that will drop down the degree in Tn by 1. So we now have P of T1 through Tn looking like this. The HI's, they're polynomials in S1 through Sn with integer coefficients if P has integer coefficients. Well, since P of T1 through Tn is symmetric by assumption in the TI's, that's here, this is also symmetric in the TI's. Therefore, we can interchange Tn and Ti for each Ti. Do this one at a time. When we do it for a particular Ti, it pulls out the Ti's, puts in the Tn's, but the coefficients don't change because they're symmetric in all of the T's, T1 through Tn. So this polynomial, where I've replaced the Ti's by x, minus our original polynomial, this has a bunch of roots. Each T sub I is a root of this polynomial. But there are n of those, T1 through Tn, and yet this polynomial has degree at most n minus 1. That's why I had to reduce the m here. The only way a polynomial can have more roots than its degree is if it's the zero polynomial. And the only way that can be the zero polynomial is if the h's are 0. And so P of T1 through Tn is all the h's, h sub i's for I bigger than or equal to 1. So so P is h naught, which is h naught of S1 through Sn. And we are done. Isaac Newton is done. Okay. That is the polynomial we want. That's the Q polynomial. And this whole process is algorithmic. Okay. Now, after we recovered, we can continue. How Newton was a smart guy. How can Newton's theorem be used to advantage in our context? Well, when trying to find the roots of a polynomial p of x, we can assume not only that the coefficients are known, obviously, if we know the polynomial, but also that all symmetric polynomials in the roots are known, because they are polynomials in the coefficients. And we know how to get those polynomials in the coefficients. So you hand me a symmetric polynomial in the roots, I can grind through Newton's proof here and hand you the polynomial in the elementary symmetric polynomials of those roots, in other words, the coefficients of p of x. Okay. So we trade in something that has the roots in it, a symmetric polynomial in the roots, for a polynomial that has only the coefficients in it, and the coefficients are known. And the key here is that the proof we just went through is an algorithm, so we can actually construct the polynomial of the coefficients. Let's try it out. Here's quadratic, monomial quadratic. Let's say it has roots r and s. We know the elementary symmetric polynomials in the roots. R plus s is negative b, r times s is c. But we also know any polynomials that are symmetric in the roots. For example, r cubed plus s cubed plus 2r squared s squared minus 3. This is symmetric in r and s. Therefore, we can grind through Newton's algorithm and compute what this would be as a polynomial in the coefficients b and c. We get that polynomial, we know what this is. Well, we don't care about this, but observe, while we cannot assume that r minus s, the difference of the roots, is known because that's not symmetric, we can assume that its square is known. So we can add that to the list, call it beta. It is a known value. It is not just known in a theoretical sense, it is computationally known from the coefficients b and c. In fact, it's not a problem to actually get that. Beta is r minus s squared, which is r plus s squared, minus 4rs, which is b squared minus 4c, polynomial in the coefficients. Look familiar? Remember, a is 1 is a monic polynomial. So this is b squared minus 4ac. So r minus s is the square root of this. And so r is 1/2 r plus s plus r minus s, which is 1/2 negative b plus square root of this business, negative square root. We have the quadratic formula.